Hello and welcome to lesson 29 of Additional Maths with Mr. Barrow. Today we're going to be looking at something called reduction to linear form. What we're going to be doing is we're going to be using logarithmic scales to reduce an exponential or a polynomial curve to a straight line so that we can see the definition over a long period of time. I'll show you with an example before we look at that worked example. So let's say that I had a bacteria, okay? So at time t0, okay? So I had one bacteria. So every second, let's say, this bacteria doubles, okay? So it replicates once every second, okay? So each bacteria splits into two every second. So after 1 second, I'd have 2. After 2 seconds, I'd have 4. After 3 seconds, I'd have 8. Etc. 16, 32, 64, 128. Okay, and I could continue and write down the number of bacteria I'd have at any specific period of time. And I could show this on a graph. So here would be the exponential graph for the first 7 seconds. And I can see the general gist of the information. So at 1 second, I can see that it's a very small amount. Okay. I need a relatively large scale on my y-axis, so for n. For my x-axis, which is the values of t, I go up to 7. I can see relative definition for all of it. But what if I continued? What if I wanted to demonstrate using a graph the first 20 seconds or beyond that? Okay, then I'd have to increase my y-axis scale. So it would look something like this. Here's the first 20 seconds. Now, the problem with this is that you can definitely get a general sense of how many bacteria there are after 20 seconds, okay? Somewhere around there, so I could read off. Okay, so that value there. And I could just about read off 16 seconds and maybe 14 seconds, but for the first 12 seconds, it looks like there were no bacteria at all, and then they suddenly appeared out of nowhere. That's because the y-axis scale needs to be so big to contain all the information that the definition at early times is completely lost. So if we want to visualize exponential and polynomial graphs, polynomial things like x squared, x to the power 3, x to the power 4, etc. If we want to visualize them over large periods of time, because they grow quite steeply, we need to do something with our normal vertical scale, okay? And so what we do is we use something called a logarithmic scale. And you will have seen this. You may not be aware that you've seen this, but you will have seen this, especially over the last year. There are lots of graphs out there with logarithmic scales to show number of cases of coronavirus and things like that, okay? You will also have heard of different things such as the Richter scale, which is a logarithmic scale itself. So the Richter scale measures earthquake strength. So if you have an earthquake with a strength of 8 on the Richter scale, and another earthquake with a strength of 9 on the Richter scale, the earthquake with a strength of 9 isn't just a little bit stronger, it's 10 times stronger. Okay, each one increase in the Richter scale value is actually a 10-fold increase in the strength. Okay, because it's a logarithmic scale, and I'll explain more in a minute with an example. Okay, so let's look at what we're actually going to be doing today. So in a nutshell, this is what we're going to be doing. We're going to be taking exponential functions and polynomial functions, very simple exponential and polynomial functions, and we're going to convert them into the form y equals mx plus c. So an exponential function will be of the form n equals a times b to the power of t, where n is the thing such as the number of bacteria, okay, or the number of cases of coronavirus, or etc. It's the value we're trying to find out. T would be the time, okay, and a and b are just some constants. So some specific values, so that they will not change. The values that will change are the n and the t. So the red letters are the variables, and the green letters are your constants. Okay, and the polynomial one, we will have n equals a times t to the power of b. So here, my unknown is no longer in the exponent. So in an exponential, the unknown, so the variable is in the exponent. Here in a polynomial, the unknown is put to a specific power. So for example, you might have y equals 7x cubed. That would be a polynomial where the unknowns are the y and the x, and the y depends on the x. And in the one above, you might have n equals 3 times 5 to the power of t. So the unknowns are the n and the t. So the unknown on the right hand side is in the exponent, so it's an exponential. Okay, so I'm going to teach you with two different examples how to convert these sorts of equations into linear forms so that then you can graph them and show definition over a long period of time because it'll turn into a straight line. Okay, so let's have a look at the first example. First example, convert n equals 4 times 2 to the power of t into linear form and sketch its graph. So we're going to use our friend the logarithm to do this. The first thing we're going to do, because we want to remove the t out of the exponent, is we're going to take logs of both sides. We're going to take the default log base 10. So I just write log, and that means that I'm using log base 10. Make sure, by the way, that you have watched lessons 27 and 28 already so that you get a good sense of what logarithms are. You're going to need that skill for this lesson. So take logs of both sides. So that will look like this. So log of n is equal to log of the entire of the right side, 4 times 2 to the power of t. By the way, I have seen A-level mathematicians, A-level further mathematicians think, oh, look at this, 4 times 2 to the power of t. I'll just turn it into 8 to the power of t. Please never do that. Okay, the 4 is not to the power of t. The 4 is multiplying by 2 to the power of t. You cannot combine that and make 8 to the power of t. That is not mathematically possible. Okay, so that is just as simple as it can be, 4 times 2 to the power of t. So it is only the 2 that is to the power of t. Okay, so now we're going to use one of our log laws to split up the right side into two logarithms. So log n is going to equal, so the first log law we know is log of AB is equal to log A plus log B. We learned that and we proved that in a previous lesson. So we're going to use that first law of logarithms to split up log of two things multiplied together. So we have 4 multiplied by 2 to the power of t. So that becomes log 4 plus log of 2 to the power of t. Next, we're going to use the third log law, that n log a is the same as log of a to the power of n. So here we have log of 2 to the power of t, so we can rewrite that using that log law as t multiplied by log 2. Okay. Now, the great thing is that now we have this in linear form. You might not think this doesn't look like y because mx plus c, but it actually does. What we have here is a constant. Log 4, if you plug that into a calculator, it would give you a specific value, a finite number, a constant value. The same with log 2. That is just a constant. So the log 4 is about 0.6-ish. The log 2 is about 0.3-ish. Okay, so those are just numbers. And the log n and the t are variables. Those values can change. Depending on what I use as my value of t, my value of log n will change depending on that. So that matches perfectly with y equals. Now, I'm going to write it in a different form, in a different order. C plus x m. You're used to y equals mx plus c, but mx is the same as xm. It's just we usually write it mx first by convention because we write the constant in front of the variable. But I'm just writing it this way so that we can really clearly see how things match up in the equation above and the equation that we are used to. So have a think. If I had to draw the graph of log n equals log 4 plus t log 2, what would the y-intercept be? What would the gradient be? How could I draw this on a graph? So your y-axis is now the log n axis because these two match up. Your y-intercept is now log 4 because these two match up and c is the y-intercept. Your gradient is now log 2 because that matches up with the m. And your x-axis is now t. It's the t-axis because that matches up. So now I can draw the graph of log n equals log 4 plus t log 2 on an axis. So I'll draw my y-axis, and that y-axis is the log n axis. So we use a logarithmic scale for the y-axis. For the x-axis, it's just the value of the time, the t. So that isn't a logarithmic scale. It's just the y-axis, which will use a logarithmic scale. And then my graph will go through at log 4, which is about 0.6, as I said, and it'll have a gradient of about 0.3. So it'll look like that. So that value there is log 4, and the gradient, so for every one across we go, it would go up by log 2. And that is what my graph will look like. That's the sketch of my graph. So, just running through it all together, we converted this function into linear form by using logarithms, and then matched it up with y equals mx plus c, and drew the graph of log n equals log 4 plus t log 2 as a straight line because log 4 will be the y-intercept and log 2 will be the gradient. Let's see if you can have a go. So I want you to convert v equals 5 times 8 to the power of t into linear form and then sketch its graph. So pause the video and have a go. Okay, for this, again, we take logs of both sides. So log v equals log of 5 times 8 to the power of t. I'll do this in a slightly quicker way. That then turns into log v equals log 5 plus t log 8. So what we have is we have our y-axis, we have our x-axis, and then we have the y-intercept and the gradient. So our graph will look like this. So the x-axis is t, the y-axis is the log v axis, as it were. The graph will be a straight line going through log 5 on the log v axis, and the gradient will be, if I go 1 across, I will go log 8 up. And that's my graph. Well done if you got that right. Okay. So that's how to turn an exponential function into linear form so that you can graph it over a long period of time. In essence, you use a logarithmic scale on the y-axis. So let's have a look now at the second type, which is polynomials. So this one, convert n equals 7t cubed into linear form and sketch its graph. So we use the same process for this. We firstly take logs of both sides. So we get log n equals log of 7t cubed. We use the first log law and we rewrite the log of 7t cubed as log of 7 plus log of t cubed. Then we rewrite the log of t cubed using the third log law. So log n equals log 7 plus 3 lots of log t. The difference with this, with the previous one, is that our variables before were log n and t. Now our variables are log n and log t. So for these types of questions, we're going to need a logarithmic scale on both axes. Our constants are log 7 and 3. So it's in effect, we have y equals c plus mx here. And so our vertical axis is the log n scale. Our horizontal axis is the log t scale. And then, if that's true, then our graph goes through at log 7 on the y-intercept, and it has a gradient of 3, okay? So for every 1 across, you go 3 up in the log n scale. So that is the graph of log n equals log 7 plus 3 lots of log t. So here, a polynomial has been turned into a linear graph, and so you can see definition over time if we use log scales for both the y and the x-axis. Okay, so that's that example. Let's see if you can have a go at this one here. Convert p equals 15t squared into linear form and sketch its graph. Pause and have a go. So what you should have is log p equals log of 15t squared. So log p is log 15 plus log of t squared, which is then plus 2 log t. So that is the function in linear form. So if you've got that right, well done. Then sketching it, you draw your axes. Your axes are the log p scale on the y-axis and log t scale on the x-axis. Your y-intercept is log 15. And your gradient is 2. So for every 1 across, you go 2 up. So that is the graph of log p equals log 15 plus 2 log t. If you got a sketch like that, brilliant, well done. Okay, in the next lesson, we're going to look at putting data into these graphs. Okay, so getting these graphs from just pieces of data and seeing if we can fit them into an exponential function, which then goes into a linear graph, etc. What you should do now is you should have a go at exercise 12.3 from this textbook. So the third exercise in chapter 12, focus just on questions 1 and 2, okay? In the next lesson, I'll teach you how to do questions 3 onwards from that exercise. So just questions 1 and 2 for now. Okay, just focus on turning exponential and logarithmic exponential and polynomial functions into linear graphs using the logarithmic function. Enjoy.